Okay, so hi everyone. So as I said, okay. Okay, this course covers 3 or maybe 4 main concepts. So what are these? So they are metaheuristic optimization, fundamentals of game theory, fundamentals of reinforcement learning, and fundamentals of fuzzy logic, if time allows. Okay. Concepts covered in metaheuristic optimization. So what are we going to cover? First off, preliminaries on optimization. Then local search, hill climbing. By the way, I have slightly, if you see the outline of the previous, this course in the previous year has changed. I have added to that, okay, for you to learn more, right? So I think if you see those outlines, the whole course may be covered half of this, and doesn't cover game theory, doesn't cover fuzzy, but I'm covering this. You might be angry at me right now, but you will thank me 3 years later, right? Okay. So local search, it's variants. Will cover different variants of algorithms, such as multi-start local search, iterative local search, guided local search, jitter or adding noise, smoothing method, variable neighborhood selection, generalized neighborhood selection, also simulated annealing, taboo search, genetic algorithm, so variants of crossover and mutation, genetic programming. These are different. Genetic algorithm and genetic programming are different, although they use the same fundamentals. Evolutionary programming, differential evolution, particle swarm optimization or PSO, ant colony algorithms and their variants: ant colony system, fast ant taboo, some bio-inspired optimization algorithms, mostly proposed by Said Ali Mirjalili. He's currently a professor in Australia. He has proposed many of this, such as gray wolf optimizer, whale optimization algorithm. We will also cover Nelder-Mead simplex algorithm. And what is this? This is a materialistic optimization algorithm, and this is implemented as F-min search in MATLAB. Who here has worked with MATLAB? Have you seen, a lot of you. Have you seen F-min search? Yeah. This is Nelder-Mead simplex algorithm. And this is different from the simplex optimization algorithm. Those simplex algorithm is for linear programming. But this is a materialistic optimization algorithm. Then we will move on to game theory. So elements of a game, we'll cover it, such as players or agents, actions, payoff or utility, information, equilibrium, I said it information twice, sorry. Strategy and nature. Well, by the way, game theory is very interesting for all fields of science, and I think people in management science often like it a lot. It's used a lot in finance and economy, like duopolies, right? We'll cover forms of game, normal form and extensive form. We'll cover 2 important equilibriums: dominant strategy equilibrium, weakly and strongly dominant, also Nash equilibrium. Do you know John Nash? No? He was a famous mathematician. Have you seen the movie A Beautiful Mind? If you haven't, go and watch it after this class. That's a great movie. Some well-known games. We will cover some well-known games. Why? Because, for example, we have a game between two agents, and you can translate it to different scenarios, right? For example, we'll have the prisoner's dilemma, which is a game between two prisoners, but you can also have it in a match. There are some matches, I think you have seen that there is some money and there are two people. They need to grab the money, right? If they both grab the money, they will lose it. If they say, I don't grab it, then it will be half between them, right? But if someone doesn't get it and someone gets it, that person who got it will got the whole money. Do you see? We have different kinds of games, such as Prisoner's Dilemma, the Battle of the Sexes. It's just, by the way, I didn't name these. These are famous names for the games. So it means that apparently in this game, there is a husband and a wife. They want to go somewhere in the evening. The husband says, I want to go maybe to gym or somewhere. The wife says, I want to go to a park. So this is a game, the welfare game, and the game of chicken. The game of chicken, do you know what is that? There are two drivers. They drive toward each other. Suddenly, one of them should go the other way. Otherwise, they will both die. Introduction to cooperative game, non-cooperative game, zero-sum game, sequential move game. So it means that I do something, then the other person does something. Then I do something, right? Bayesian games, which they work with probabilities. Mixed and continuous strategy. So we will see what these are. First order condition. It means that we take derivative, set it to 0. We will see that. And payoff equating methods. Also, we'll see equilibriums in duopoly. Especially, this is very useful for management science. These are you might have heard of this if you are studying management and economy and finance. So it's Cornut, Stackelberg, and Bertnar games. We have dynamic games with parameters. So when we have some parameters and we want to determine the parameters in the game. Repeated games, when the game is repeated. We'll have several strategies such as Grimm strategy, tit-for-tat strategy, Folk theorem, minimax and maximin strategies. If you know a bit about machine learning, if you have heard of GAN, generated adversarial networks, that's a minimax or maximin problem. Then reinforcement learning, just fundamentals. Elements of reinforcement learning, such as environment, action, state, reward, policy, Markov decision process. We'll cover Bellman's equation, then value iteration and policy iteration, then Monte Carlo evaluation, then temporal difference evaluation, Q function, Q learning, gradient Q learning, deep Q network or DQN. It was used for solving Atari games, so playing Atari games. Policy gradient, reinforced algorithm, which was one of the very first algorithms in reinforcement learning, and brief overview of playing game of Go with reinforcement learning. Also, the concept in fuzzy logic. So, we will cover elements of fuzzy logic such as membership function, symbolic representation, fuzzy union, fuzzy intersection, and fuzzy complement. What is fuzzy, by the way? Fuzzy logic says that when I ask you, are you feeling well or not? What do you say to me? You can either say, I'm not feeling well, or I'm feeling well. That's binary logic, right? 0, 1. But you might say, no, I'm 70% well, right? You're neither good nor bad. You're 70%. You're somewhat well, right? When you have continuous range, then this is fuzzy logic. So you can extend binary logic to become fuzzy. This is what we have. And it is used a lot in various fields of science, especially control. We have fuzzy controllers. I think mechatronics students know about control a lot. T norm, S norm, fuzzy relation, compositional rule of invariance, max mean, max product, fuzzy invariance, fuzzy rules, fuzzification, defuzzification. What does it mean? So when I have in this world, the values are crisp. What does it mean? It's not in the world of fuzzy. When we go from this world to the world of fuzzy, we need some translation. That's called fuzzification. When we want to go back from the fuzzy world to the real world, that's defuzzification. We need to defuzzify it. And there are several methods for these. We'll cover them, cover the important things. Then we'll cover fuzzy invariance system, which are several models. Mamdani fuzzy model, Sugeno fuzzy model, and Tsukumoto fuzzy model. And I think, as it's obvious, these are Japanese names because in Japan, fuzzy logic was improving a lot. I heard that even their subways were controlled by fuzzy controllers. Okay, by the way, I forgot to say a little bit about reinforcement learning. So, what is reinforcement learning? Assume I want to teach a dog, right? So, what do? I want the dog to, whenever I come to the house, I want the dog to come to me, right? The first time I come to the house, the dog doesn't come to me. So I give it hunger. I don't give the reward to it. So it's a negative reward, right? I don't. Next time it learns to come to me, then I give them to eat, right? So after some trials, it will find out that it should come to me for it to be given some sweets, right? This is exactly reinforcement learning. We have positive rewards, negative rewards, right? So the same way that we teach animals, such as dogs, we can teach machine. Assume the machine, when I say machine, it's a mathematical model. It has some parameters. Let the machine or the mathematical model be the dog. Then I will tell that initially the machine learning model or the mathematical model will do something wrong. If it is good, I will reward it well. If it is not good, I will not reward it. Or I will reward it negative reward. Then it will find out that it should do the correct things. But how does it find out? That's optimization. Hide it from me that all machine learning is optimization. All machine learning is optimization. So we have some parameters and we need to learn them. How? Using optimization. And we do it by optimization. So that was reinforcement learning. A little bit explanation for game theory. What does it mean? Assume I have two agents. And they want to do something. Each agent has some payoff or utility. And each of them, they want to selfishly increase their utility, right? And as you see, they are playing a game. We enter a game because we want to increase our utility. However, after some time, we might find out that no, we shouldn't be so selfish. If we are both selfish, or if all of us are selfish, we will gain nothing. We have to collaborate or cooperate with each other. A nice example of that is that movie scene in the movie A Beautiful Mind about John Nash. I'm saying this scene from the movie. I'm not making it up, so don't think of it as a controversial. This is a movie thing. They are in a bar. John Nash and several friends, several males are in the bar. Several females come in the bar and listen to this mathematical thing. Then they will say one of the girls is very hot, and they will say to each other, let us get the hot girl. All of them are talking to each other. They're arguing. They are selfish. They want to increase their utility. Then what happens? Suddenly, John Nash thinks very deeply about it, and he tells them, if we do that, we will lose everything. Why? Because if we all go to the hot girl can't have all of us. She will probably reject all of us. Then we'll go to the other girls, but the other girls will also reject us because they don't want to be second. Right? So John Nash told his friends, let's not go to the hot girl. Let's ignore her. Let's all of us go to the other girls. Each of us goes to one of the girls. In this way, we'll have our girls, right? Do you see? They are collaborating with each other. They are cooperating with each other. And they are increasing their utility. Did you get the understanding, the deep understanding of Nash equilibrium? Okay. Also, metaheuristic optimization. I will briefly talk about it, but just a brief introduction. What is that? Assume I have some cost function. I want to optimize it, right? And then there are two ways at least to do optimization. One of them is classical optimization. The other one is metaheuristic optimization. Classical optimization is optimization using mathematics. If you are crazy for mathematics, I think you will like classical optimization, such as gradient descent, such as Newton's method, such as interior point method. These things, right? However, sometimes the cost function is too complicated, or you have too many constraints. An example is what? Optimizing the aerodynamics of an airplane. Too complicated. Too many constraints. Or if you have a robot which is too complicated, it has too many degrees of freedom, then maybe classical optimization will be frustrating, either for you or for the computer. Then, in these cases, you might want to relax your interest for mathematics. I will say, okay, forget mathematics, let's do search. Let's do search to find the best solution in this optimization problem. Now, there are several ways to do search. How? One way is this. One way is you say, let's search randomly, blindly. So I have some cost function. Blindly, let me try several solutions and see their cost value. And the one which has the minimum cost, I take it as the solution. Is it a good approach? More or less. Not much good approach, right? Because you might completely miss the optimum solution, right? If you do that, maybe your airplane will fall. Then what do you do? So another way is that you do grid search. What does it mean? Grid search is this. I think I have it here. Let me bring it. Let me bring it. So this is the complicated cost function. Do you see this? It's too much complicated, right? Compare it with a simple cost function above, right? Then probably you say, let me do search. But for you to do search, you need to either randomly search or do grid search. This is grid search, also called brute force search. What does it say? It says, let me have a grid of solutions and try all of them. So like this, with some step. The finer the step, the more accurate I am, right? So this is 1D. In 1D, it might be easy, might be reasonable. The more dimensions you have, the more complicated, right? For example, in 2D, what happens in 2D when you have x1 and x2? What do I mean by 2D? You have two variables. Here you have one variable, right? When you have two variables, then your grid will be like this. Then you need to check all of these points. If it is 3D, you will have cubes, right? And you will see the number of points will increase a lot when you have high dimensionality. Therefore, grid search or brute force search is not also optimal, right? In terms of time complexity. Then you will say, let me not do random search because it's not accurate. Let me not do brute force search because its time complexity is not good. Let me search wisely. What do I mean by searching wisely? This searching wisely is called metaheuristic optimization. I think by an example, I can tell you what wise search is. Assume here in this room, there is some treasure in the ground of this room, somewhere, but we don't know where. We are some people, a few people in this room. We want to collaboratively find this treasure under the ground. Again, one way is we randomly choose some points in this room and we dig, right? Another way is we have a grid and we dig every point, but its time complexity is bad. Then another way is let's do a wise search. How? I choose a random point, you choose a random point, you choose a random point, we dig, right? Maybe I find some gold, maybe you find some gold, maybe I find some plastic, maybe you find some diamond, right? So assume we are three people. Compare plastic, gold, and diamond. Which one is more important or more valuable? The diamond, right? Then gold, then plastic. Then a wise search is that we two, you found gold, I found plastic, the other person found diamond. We should move toward that person who found diamond, right? Because probably the treasure is there, because that person found the diamond. However, we shouldn't all of us go exactly where that person was. Why? Because maybe there is a better treasure here around. We don't know. Then, therefore, we move a little bit toward that person, but not too much. You also move toward that person, but not too much. And then that person also searches locally around. Then we dig again. We dig again. We dig again. Maybe now that I found in the previous iteration, I found plastic. Now suddenly I found, let me see, 2 diamonds, something more valuable than 1 diamond. Then I say, by the way, I found 2 diamonds. Then you two will say, okay, now the global best is 2 diamonds, right? 2 diamonds is better than 1 diamond, better than gold. So you two now move toward me a little bit. We do it iteratively until we find the best treasure. Did you see the wise search? This is one of the algorithms called particle swarm optimization. There are a lot of different algorithms for metaheuristic optimization. This was one of them. Here in this cost function, for example, we are assume these are 3 points. This is the lowest cost. So these two move toward this person, but this person also searches locally around itself, right? So I briefly talked about the 4 things which we are gonna cover. The course materials, lecture notes will be provided to you. I will put the lecture notes to the learn, and but I might update them before the classes. Also, we have a YouTube channel. Hopefully the voice is good. I will put it, and feel free to subscribe. Yeah. And also, I have some tutorial papers, although maybe only one of the tutorial papers will be useful for this course, but feel free to check out my tutorial papers, some of which have become chapters of a book. We have Piazza of the course. Please enroll in the Piazza of the course. So go to Piazza and search EC 457A and enroll in it. I have put a poll there. That's for tutorial sessions. As you know, we have tutorial sessions for this course, and the tutorial sessions will be held by Daniel, one of the TAs. So Daniel is wondering whether you want the tutorial sessions to be online. So there are 3 options. Either it's online in Microsoft Teams, but it will be recorded, but it will be 50 minutes. In Mondays, 5:30 to 6:20. Or in person here, again, 5:30 to 6:20, it will not be recorded. The third option is that pre-recorded, but it might be more than 50 minutes. So your choice. Please let us know your opinion, and we'll decide based on that. Also, and I appreciate if you do it soon, because we need to decide about it. We have the Learn page. Check for the notifications. There are some additional books. So for Metaheuristic optimization, by the way, for this course, you don't need to read the books. Optional, right? For more interested students. But I think the lectures will be self-explanatory. So this book, Metaheuristics from Design to Implementation, by El Ghazali Talbi, and another book, Computational Intelligence and Introduction, by Andreas Engelbrecht. Both of these are available. Their PDFs are available in ResearchGate. If you search this, you will find them. For game theory, there is a book, Games and Information: An Introduction to Game Theory, by Erik Rasmussen. For reinforcement learning, by the way, the PDFs, the chapters of this book also are available in this link. Reinforcement learning, the book of Sutton, I think that's the most important book in reinforcement learning. For fuzzy logic, there is a book, I think it's good, it's explanations, but the PDF is not available. Again, these are not mandatory, optional. Soft Computing and Intelligent Systems Design Theory, Tools and Applications, by Carey and Silva. And also research articles in the literature. Courses website. So I'm Benjamin Gojok, and this is my email address. Your TA is Daniel Sadrianzadeh, the email address, and also Juan Rui Zheng. This is the email address. Also, please message us in Piazza if you have any questions or think. You can message either publicly or privately or anonymously. All of them are available for you to choose. Because I think Piazza is better for us to answer better than email. Classes will be in person. Discussion, chats, and questions will be in Piazza. This is the courses website, although I will update it seldomly. I will update things more frequently in Learn. I will also probably upload the videos to my YouTube channel if the voice is good and these things. Okay. Course evaluation, assignments, 30%. So we will post them on Learn, and I think we will have. I can't promise a number of assignments, but I think it will be 2 to 3 assignments. I can't promise a number. It depends on how it goes on. We'll have a course project 20%. So close to the middle of the semester, you will form teams and you will upload a proposal. The proposal will not be graded, just for us to check what you are working on. And after we say that's fine, then you will work on it and you will submit the course project report and codes. In other courses, I usually ask for them to present in the last day of the semester, but I think in this course it's not feasible because there are more than 100 students. And more details, we will say that in the Learn. And as I said, you need to pick a topic related to the course. And the final exam, 50%. This is not my choice. If it was my choice, I would have a midterm exam, and I wouldn't have a final exam, but this is mandated by department. Okay, so we'll have 50% final exam, but because I think this is a core course. Date will be announced by the department. Again, if they don't force me. So there is an if. If they don't force me, it will be open book. If they force me, I might do something else. I might give the formulas in the sheet because I don't want you to memorize. I hate memorization. So bonus points: participation in class, participation in the discussions, asking questions and answering questions. Please participate. I don't want to be the sole speaker. I actually hate those classes that only the instructor talks. See me as your friend, okay? Don't see me as any professor or these things. Call me Benjamin, whatever you want. See me as your friend. We are learning together. Okay. And I think the age difference is also small, so you can see me as your friend. I'm 30, by the way. And don't worry much about your marks. As I said, I'm a good grader. As long as you do your best and do all the tasks. If required, if needed, I will curve the grade. Okay. This is my approach. Okay. Again, look at this. So what? I don't know if you have watched any online courses on YouTube, for example. Have you? For example, physics in Stanford. Have you? I do that a lot. I actually learned much more from YouTube than university. And when you learn from, for example, YouTube, do you care about your grade? No, you only care about enjoying course, right? Do it exactly here, right? I don't mean that you don't come to the class and watch it on YouTube. No, I don't mean it. Come here and enjoy the course. Enjoy the course. Don't worry about the grades and do your best. Okay. Focus on understanding, and we'll try this to be useful for both industrial projects and academic research. We'll have some theory, and also we'll try this to be useful for practice. Ask questions, and I don't want to be the sole speaker. This is, I repeat it. Okay. By the way, you might be wondering, how can we cover all of these things one semester? The answer is that I usually will remain until the end. Okay. But we have, what do I mean? So there is 3-hour courses. We'll have break. We'll have a quarter break, almost in the middle of the classes, but we'll usually stay until 9:20, right? Yeah. 9:20. We'll stay until you might be saying why, because I think the other people who don't do that, they are not teaching you sufficiently. Okay. if you want to be taught sufficiently, you need to stay and learn. This is my philosophy. For me to be able to cover most things that I want to teach, I need to stay until the end. Unless something happens, for example, unless I don't have the slides ready or this. So, any question before we continue? So, what? No.
It said you've been a model here since 2017.
I was a student, PhD student. So I graduated, I think 2 years ago. I graduated my PhD 2 years ago. Yeah, maybe 2 years and a half. I don't remember. I think it was February 2021. And then I did 1 year of postdoc and then industry. Okay. Just I remember when I had classes in Waterloo, I had a course in computer science department optimization. The course was full, the classroom was full. So, but for me, it was the most important thing was learning. So I used to come and sit on the ground in front to be able to see the blackboard. I remember that. But yeah, good time. Okay, so we'll have the break, but I think it's good time to have the break. Maybe we come at let's say 10 to 8. No, not good. Because I want to cover things, but okay. Maybe in 5 to 8. 5 to 8 will come back. If you guys know how to do that, let me know. Okay, by the way, before we start the real thing, what's your opinion so far about the course? Have you liked it? Yeah. Yeah. Okay. Great. Thank you. So, okay. Great. So, preliminaries on optimization. What is optimization? Consider a function representing some cost, right? Okay. We call it cost function or objective function. These are different names for the same thing, right? What is the cost? Can be anything. Can be anything, some L. We want to decrease it, minimize it. We want to minimize this cost function, or sometimes it's the other way around. This is something we want to maximize, right? Some such as benefits or utility, right? Example for minimization. The cost function can be error of some airplane structure from the perfect aerodynamic structure, right? Example, by the way, I will upload the annotated slides also, okay? So both slides and annotations, they will all be uploaded to Learn. Example for maximization. It can be a profit of the company, for example. And also, if you see closely or with sharp eyes, you will see that all life is optimization. You are either minimizing some harm or maximizing some benefit or utility in our lives. It's always like that. All life can be described as optimization. But this optimization is very complex, right? And also, all machine learning is optimization. I can prove it to you. So there are several categories of machine learning. One of them is classification. What is classification? We have several classes and we want to discriminate them, right? So classification is an optimization. And what is that? It says let the error be the confusion of the classes. I don't want them to be confused, the classes. Therefore, I optimize it. I optimize my mathematical model so the classes are discriminated well enough. If it is regression, regression is predictive. You can see it as predicting a float value, a continuous value, such as weather prediction, the stock prediction. You also, what is your error here? The error of your prediction from the actual value. For example, you predict that the weather tomorrow will be rainy, but tomorrow it will be snowy or hot. Then what happens? You have some error. And then you will optimize it. You will make your weather prediction module better, right? Or the machine learning can be clustering. You have some clusters. You have some data, and you want to cluster them or group them into several groups or clusters based on their patterns. Okay, then your cost can be what? Minimizing the, so if 2 points or 2 data instances are in the same cluster, their patterns should be similar. So the error can be difference of points within the cluster, right? You should minimize it, right? 2 what?
Right.
Yeah. Please participate in the discussion. Exactly. So classification, regression, clustering, and then we have reinforcement learning, again, rewarding. You can see that. You can see it as optimization problem. Then what else is in machine learning? Yeah, I think this. So all machine learning is optimization. And variable of objective function, because every objective function has some variables, right? Every function has some variables, input variables. We learned it in high school. Do you remember? X, we feed it to some function f of x. This x might be univariate, might be multivariate, right? When I say multivariate, it means that it has several dimensions. Univariate, it has one dimension. And then these these variables are called objective variables, also called decision variables, also called optimization variables, or argumental variables, argument of optimization. And so here, for example, f of x is x squared. X is the optimization variable, right? Here, x is univariate. And by the way, decision variable is usually used when it is linear programming. They usually call it decision variable. Okay. Here, it can be univariate or it can be multivariate. When it is multivariate, then we have several values, right? Then your optimization variable is a vector, right? Here, in this case, it is an n-dimensional vector, right? And by the way, I will explain every notation that I use. I don't want anything to be confused. And if I miss anything, ask me. Okay. What is this? This is transpose. And why do I use that? Because this is a row vector, right? I usually in mathematics, denotes the vectors as column vectors, usually. Okay, so I want it to be column vector. What does it mean? It means that it's like this, x1 to xn, right? When I say x transpose x, we'll see inner product also in a few slides. But when you see this, it's inner product. So you say it's like x1 squared, so x1 times x1 plus x2 times x2 until xn times xn. For example, if here it is 2-dimensional, then this becomes like a bowl. This is x1, this is x2, and this f of x is a scalar, right? Because this is a scalar. X, as you see, is a vector. The variable is a vector. However, f of x here is a scalar. Therefore, I can denote it in 3D, right? x1, x2 as input, and f of x as output. If you do that, then it becomes like a bowl. That's why they call it is quadratic. It's a quadratic form. Quadratic form is like a bowl. If you look at it from above, from top, right, it will be like this. What are these? Every line here, it means that the cost value is the same. So along these line, the cost is the same. You understand what it means? So it means that here the cost is the same. Also here the cost is the same. It means that it's coming up, right? Or it might be going down. It's not obvious, but when you look at it in 3D, it's obvious that it's going up, right? The optimization problem can be unconstrained. What does it mean? It means that you minimize some function, just this, or maximize, minimize or maximize function. This is exactly what we learned in high school or college, depending on where we studied, in which country. In high school or college, we learned that what do you do for this when you want to minimize some f of x with respect to x? Okay, exactly. Take the derivative and set it to 0, right? Set it to 0. So this gives us the extremums of the function, and the extremums can be minimum, maximum. Also, it might give us saddle points. We will see that. We will see that. What do I mean? Consider this function. If you take derivative, set it to 0, it will give you these 3 points. This is minimum, this is maximum, and this is saddle point. How can we find out that whether this is minimum or maximum or saddle point? What? Say it. You were saying second derivative. Yeah, exactly. We use the second derivative. Here, the second. What does the second derivative tell you? Yes, yes, I can say it in other words. In other words, saying that it says where the ball is facing, whether this is like a ball, right? Whether it's facing upwards, right? Yeah, or facing downwards. The ball, okay? When I say ball, you can see it as a multidimensional ball too, right? Hyperbole in multidimensional space, whether it's facing up or facing down. If it's facing up, its second derivative is, if it is univariate, it's positive. If it is multivariate, the second derivative is a matrix and it is positive semi-definite. If it is facing down, it is negative semi-definite. Right? And so, simple for finding out how to solve the unconstrained problems. Take derivatives set it to 0. We learned it in high school. However, what if I set it to 0 and I can't find the closed form solution? What do I mean? For example, x squared, its derivative is 2x equals, set it to 0, x equals 0. It's closed form solution. However, if you have something very complicated, tangent of x over square root of, I don't know, something, sine of x squared, something. Then you take derivative of this, it becomes much more complicated, then set it to 0. Can you find x in one of the sides of the equation? No, you can't. Then what? How do you solve it? What? MATLAB. Okay, how does MATLAB solve it? Assume if you use F-min search, that's the Nelder-Mead simplex algorithm, which we'll see. However, there are some other functions in MATLAB also which do that. But if you want to do it on paper, how do you do that? Trial and error. Yes, but there is a wiser way to solve that. Have you passed numerical analysis or numerical computation course? Yeah. Yeah, exactly. Newton's method, for example, or gradient descent. So you need to do it iteratively. You need to do it iteratively, but depending on whether you use the first derivative or first derivative and second derivative, it's either first order optimization or second order optimization. If it is first, for example, gradient descent is first order optimization. Second order optimization, such as Newton's method, such as interior point. These things. By the way, if some of these names are unfamiliar to you, I will not quiz you on the things that you don't know. I will explain everything. If I want to ask you anything, I will explain it completely. But sometimes I have to pass from some concepts fast because they are out of the scope, but they are related, such as interior point method. Interior point method, you might find its name scary, but it's very simple. It's saying that have you heard of Newton's method? Newton's method is using first order derivative and second order derivative for iterative optimization. Okay. However, that's for unconstrained problem. What if I have some constraints? Then they generalize Newton's method. They call it the interior point method. For more information on that, which is out of the scope of this course, refer to my optimization course on YouTube. That's classical optimization. Okay. So here, the optimization problem can be constrained, like this. These are the constraints. Let's take a look at this. So I have some function, some quadratic function. My optimization variables are x1 and x2, the elements of the vector x, right? And I have two constraints here. As it is 2D, I can visualize it. For example, the first constraint, x1 plus 2x2 equals 8. This is a line, right? And this is the line. And as it is equal, I have to be on the line. I need to satisfy the equation of the line. So I'm on these points, one of these points, right? Now take a look at the second constraint. This is a quadratic function. You can find 3 points by putting points in it, right? For example, if you put x1, set it to 0. What happens? x2 squared is less than 16. Then x2 is less than or between -4 and 4. So you found these 2 points. You can also find this point by setting x2 equals to 0. Then 2x1 is 16, so x1 is less than 8. So 8 is also found. You have 3 points, so you can find the quadratic function passing through these 3 points, right? Then I need to satisfy this inequality. Should I be outside of this quadratic function or inside? I can simply put one of the points in one of these regions. For example, 0, 0 in this inequality. 0, 0 satisfies this, right? Therefore, I have to be inside. Now, I have to satisfy these 2 constraints simultaneously at the same time. So I have to be on the line and I have to be inside the quadratic function. So I have to be here. Now this is satisfying the constraints. Now let's see the cost function. The cost function is quadratic. x1 squared plus x2 squared. As you see, by increasing x1 and x2, this cost goes up, right? Therefore, it's going up like this, right? Do you agree with me? Also going up like this. Sorry about that. So it's going up like this. Also here, it's going up because it's a square, right? Therefore, then we can find out, solve it, that one of these points, in one of these points here, this is minimized. This is minimized. I think if we solve it, I think you will find some point close to here. So one of these points. Okay. That was just an idea for you to understand what is constraint optimization. So it minimizes or maximizes some cost function while satisfying some constraints. And the constraints can be either equality constraints or inequality constraints. And the inequality constraints can be less than or equal to or greater than or equal to. Right? Ask me whenever you have any question. I passed from this slide fast because I already explained that very fast. So if it is a simple enough cost function, I can use classical optimization, such as gradient descent, Newton's method, interior point method. However, if it is complicated or too many constraints like these, then we can do a metaheuristic optimization. when it is complicated, we can do two things. So when I say complicated, it means that it's also called highly non-convex. We'll see that. We'll see that in a few slides. Okay, this is highly non-convex or highly non-linear. Then, or when the gradient is too hard to compute. What do I mean by gradient? Derivative. Gradient is another name for derivative. Okay. Do you remember what I said when you have unconstrained optimization problem, what do? You take derivative, set it to 0. If you don't find any closed form solution, you do iterative optimization, right? Gradient descent Newton's method. For all of these, you need derivative. So for classical optimization, you always need derivative. What if the cost function is too complicated that you can't even calculate the derivative, right? That's another case that you need metaheuristic optimization, right? Because metaheuristic optimization usually doesn't do any gradient, usually, right? Also, another case, what if you have a black box? Your system, especially if you're a system designer, your system is a black box. You don't have access to inside it, especially when you want to do reverse engineering, right? Then you don't have access to inside the box. And what do? You can only feed some inputs and get some values, outputs, right? Then in this case, you also need to do metaheuristic optimization. Because for having derivative, for calculating derivative, you need to have access to the function inside, right? Rather than metaheuristic optimization, when you can calculate derivative and when it is not a black box, you can do another thing too. That's called non-convex optimization. There are some methods for that. For more information on non-convex optimization, you can see my course on classical optimization on YouTube. Again, when it is too complicated, we can do grid search or brute force search, but that's either not accurate or it's not efficient in terms of time complexity. So we do wise search or metaheuristic optimization. And I gave you an example of finding a treasure in this room when we find a treasure collaboratively using particle swarm optimization. Okay, now preliminaries on metaheuristic optimization. When the problem is complicated, a heuristic method approximates its solution. Okay. It gives a good enough guess of the solution to the problem, but you may not really know how good it is. So you guess the solution. That's called heuristic method. Okay. Heuristics are often problem dependent. So for every problem, you design some heuristic method. However, metaheuristics, are problem independent that can be applied to a broad range of problems. So they don't care so they design some metaheuristic optimization algorithm and they don't care on what you want to use that. That's why they call it meta-heuristic. Okay. And meta-heuristic optimization methods can solve various complicated optimization problems using wise search. Meta-heuristic methods are considered as a family of soft computing. Do you remember I said at the start of the class that soft computing is a field of science covering meta-heuristic optimization, fuzzy logic, etc. Any question? No? Okay. So we have cost and we have fitness. What are these? We usually want to minimize the cost function, right? So when we want to minimize, we usually call it cost function. But when we usually want to maximize something, we usually call it fitness function. So it's the other way around. And interestingly, we will see in a few slides that cost can be converted to fitness. Fitness can be converted to cost. In other words, when you have a minimization problem, you can make it maximization. When you have a maximization problem, you can make it minimization. They can be converted to each other. But when usually when we say fitness function, we want to maximize it. When we have cost function, we want to minimize it. Also, the cost or fitness function are called sometimes landscape or optimization landscape. Why? Take a look at this. This is like a cost function. Assume there are two variables, x1, x2, and the height is the cost. I want to minimize this cost. So I want to find this minimum, right? Here. If I want to maximize it, I want to find here, right? Then, as you see, it's like a landscape with valleys and mountains, right? Hence, they name it also optimization landscape. It's either for cost or, yes, fitness. By the way, whenever you have any question, don't raise hand, just ask.
Between like for maximization and minimization problems, are the methods the same or is it just problem dependent, whichever one?
You mean
Choosing between aiming for fitness or for cost?
yes?
Like when you pick one or the other, you said you can convert them between them.
Yes.
So to pick which one you want to be aiming for, are there like different methods for optimizing for one state, or is it just problem dependent with one state?
Okay, so the question is, why I repeat the question for this to be recorded, because it might not. So the question is when to use minimization or when to use optimization. Is it problem dependent? I can say rather than problem, it might be problem dependent, but rather than problem dependent it is more algorithm dependent, because we have various algorithms for doing optimization, and some optimization algorithms are suitable for minimization. Some optimization algorithms are suitable for maximization. Then, for example, you have something which is easier to minimize something. Then you have a maximization problem, so you convert it to minimization and you fit that to that algorithm, right? So it depends on the algorithm mostly. For example, when you have in classical optimization, when you have gradient descent, this is for minimization. When you convert your problem, the gradient descent becomes gradient ascent actually. So it depends on whether your algorithm is minimizing something or maximizing something, right? We will see. But in metaheuristic optimization, it's usually not that much hard because, for example, you usually compare things. So if it is maximization, you want it to be higher. When it is minimization, you want it to be lower, right? So in metaheuristic optimization, I think it's not a big deal. But again, it's dependent on the algorithm. Any other question? Again, as I said, see me as your friend. Don't need to raise hand to ask questions. Just ask, okay? And there are two important concepts in metaheuristic optimization. One of them is exploitation, and one of them is exploration. I think by the name, you know what these are. We use them a lot also in real world language. So what do I mean? So whenever I have some optimization landscape, okay, I'm somewhere in this optimization landscape. If I search locally around me, this is exploitation, right? Because I'm just searching locally. But when I move to different places, jump in this landscape, move to different places to see different parts of the landscape, that's called exploration, because I'm exploring landscape. Now, why are these important? You need to have a kind of trade-off between exploitation and exploration. Because if you have too much exploitation, what happens? Can you tell me? So I have too much exploitation in my algorithm. Yes? Exactly. You will get stuck in a local best. I call it local best because it might be local minimum or local maximum depending on whether it's minimization or maximization. So you will get stuck in your local best. You will not, what if you have a better solution somewhere else in the landscape, but you never see that because you're only exploiting. What happens if you do too much exploration? What happens? It's kind of the same as random search, exactly. So because you never settle down to see whether you are finding some good solution or not. Whenever you find something, you jump to somewhere else. You need to have a trade-off between this. Exactly in life. In life, if I exploit only, I don't see the world. I don't see it. If I only do whatever is given to me. What if I have some other interest in other field? I never saw that. If I only jump, young people do that a lot. If I only jump and I want to experience different things, then what happens? You never settle down. You never find out. For example, I jump from this major to another major. You never get a degree. For example, right? So you need to try. As I said, these when you learn science, you learn also how to live. Learn how to live. Also, something I forgot to say: local best and global best. Local best is that, like here. Here, for example, all of these points are local best, but only this is the global best. These are local minimum. This is the global minimum. You want to find the global minimum, right? Here, these are, all of them are local maximums, but only this is the global maximum. I want to find, oh no, assume it doesn't go up. Then I want to only find the best maximum. However, just jump into machine learning a little bit. This cost function, I actually got it from a paper in deep neural network, okay? Deep learning. The cost functions in deep learning are like this, very complicated. Very complicated. Now I have a puzzle for you, because I think this puzzle will let you understand how deep learning is. By the way, deep learning, for those of you who don't know deep learning, you have some neural network, you have some, let me add some page here and explain it a bit, because I think this is very important. So you have some neurons. Like this, right? The neurons are connected to each other. You have layers of neurons. And these connections have some weights, W1, W2, W3, right? And you want to learn these weights. And you have some loss function here at the end. Some loss or cost function. So cost is also sometimes called loss or loss function. You want to minimize. Again, back to your question. You said, for example, whenever you are dealing with deep learning, you don't maximize. Because all of the deep learning libraries such as TensorFlow, PyTorch, they always minimize. So when you have a maximization problem, you have to convert it to minimization. For example, in probabilistic deep learning, you want to maximize the likelihood, of data. However, you can't. Neural network minimizes. Therefore, they add a minus behind that. We'll see how these techniques. We'll see them. Then they call it negative likelihood. So let's minimize the negative likelihood. It's equivalent to maximizing the likelihood, right? So that's an example for your question. Here, now the puzzle, the interesting puzzle. Assume that usually the cost functions are straightforward cost functions. For example, if it is a regression problem, so you have assumed y hat is the output of your neural network for some input. And y is the actual label. So you want to minimize this. This is a norm. I will explain norm a little bit later, but assume for you not to be confused, I don't use norm. So assume like this. yi hat minus yi squared. I want to minimize this. Okay? If you see its cost function, it's very complicated, such as this. May I ask why? Isn't this loss function straightforward? Actually, this is convex. This is quadratic. This is quadratic. Like both. Then why is this cost function too complicated? It's not actually like this. Why? This is puzzle. If you understand this, or if you answer this, it means that you have understood deep learning. You give your guesses. If this is wrong, that's fine. The cost is quadratic, but when you see the cost, the loss function is the quadratic, but the cost is very complicated. Let me tell you the answer, and I think you will enjoy it a lot. This is because what is your optimization variable? You're minimizing is this with respect to what? With respect to what? Weights, W1 until W maybe 1000, whatever, right? So 1000 optimization variables. This loss is quadratic with respect to y and y hat with respect to the output of the neural network. But the optimization variable is not the output of neural network. The optimization variables are the weights. With respect to the weights, it's very complicated. With respect to the output of network, it's convex. You see that? Now, do you see the beauty? Okay. So local best, global best, I explained that. Let's move forward. Preliminaries on sets and norms. Convex set and convex Hall. A set D is convex set if it completely contains the line segment between any 2 points in the set D. What do I mean? I have some set D like this. It's a set, right? It's a set. Take 2 points, any 2 points in this set. Connect them by some line, right? By the way, this is 2D. It can be multiple dimensions, right? Still, you can connect those 2 points with a line in the multidimensional space. If that line is completely contained in the set is convex set. However, this is a non-convex set, for example, because this line is not completely contained in the set D. You see that? And I can, what is the equation of this line? It's this. Tx plus 1 minus t times y. You see that's a lot in optimization. X is this point, y is this point, and by sweeping t from between 0 and 1, you move from y to x, right? If you set t to 0, what happens? This becomes y. If you set t to 1, this becomes x. So if you change t between 0 and 1, you are moving on this line. If this line is completely contained in D for t between 0 and 1, then it means it's in the set. Then this is a definition of convex set. Okay, an example of non-convex, we saw that. Also, when we have with a non-convex set, we can convexify it. We can relax it to become convex. How? Simply, in simple words, assume you have, I forgot the word in English, but rubber, right? No, rubber. Yeah. Rubber. What? Plastic rubber. Plastic. Elastic band, whatever. Yeah, elastic band. Put it around the set. This is exactly the elastic band, right? This is the convex hull of D. Okay. This is the smallest convex set containing the set. This is the definition of convex hull. The smallest convex set which contains the set. Okay. Now inner product. You can denote, so assume you have two d-dimensional vectors, x and y. By the way, what does this mean? RD, it means that a d-dimensional Euclidean space or Cartesian space. Cartesian is representation, but let's call it Euclidean space. So this is a two-dimensional Euclidean space. This is a three-dimensional Euclidean space, right? When I say RD, it means that d-dimensional Euclidean space. And every point in this space is represented by a d-dimensional vector. So I have this. So dot product or inner product between them is denoted by this or this. So it's just, it means that x1, y1 plus x2, y2 until the end. So you multiply the corresponding elements and then you sum them. As you sum them, it becomes a scalar, right? So the inner product, the output of inner product is a scalar, although its input are two vectors. So it gets vectors and it outputs a scalar. We can have inner products for matrices. I think you already knew the inner product of vectors, but you might not, you might be unfamiliar with the inner product of matrices. It's denoted as this. Consider two matrices X and Y. By the way, in this course, when usually I denote scalars by a small letter, vectors by bold small letters, matrices by bold capital letters. Okay, so that's why the matrices are capital here, X and Y. What does this mean? In simple words, it means that a matrix with D1 rows and D2 columns. Okay. In more complicated words, for those of you who want math, you can see that as the outer product of two Euclidean spaces. Okay. And let xij be the ijth element of X, right? The ijth element, the row I, column J. Then the inner product between X and Y is trace of X transpose Y. First off, what is trace? If you don't know it, that's fine. I'm telling you. Trace of a matrix is defined as summation of its eigenvalues. I assume you know this because I think you're in the last year of mechatronics or other majors. You have seen a lot of eigenvalue decomposition and these things, right? So it's the summation of eigenvalues of the matrix. Equivalently, you can see it as a summation of diagonal elements of the matrix. Okay, so trace, you can see it as a summation of that because you always the input of trace is a square root. The number of rows and the number of columns is the same. Therefore, you can have a diagonal and you can sum the diagonal, right? This is trace. Why do I use trace? I want you to understand the philosophy of everything. Why? Why do I use trace of X transpose Y? However, I didn't have any trace in for vectors. Because what is X transpose Y here? It's a matrix, right? It's a matrix. X is a matrix, Y is a matrix, X transpose Y is a matrix. The output of inner product should be scalar. For converting a matrix to the scalar, I have to use a trace. However, for vectors, it was already scalar. Okay, then you can see it as the multiplication of the corresponding elements and summing up. Norm. A function, this norm denoted by this, it takes a d-dimensional. For you can have norm for matrices too, but here for vector, it takes a d-dimensional vector. It outputs a real value, a scalar. Right? It's called a norm. It should satisfy 4 different things. These 4 characteristics are also used as the characteristics of a distance metric. Why? Because I will tell you that you can see norm for distance are almost equivalent. Okay. First off, the norm of X should be non-negative. It's either 0 or positive. Also, when you multiply its input by a scalar a, you can bring it out, but it needs absolute value. Why? Exactly because of the, yeah, but you can also say because of the first characteristic. The first characteristic said the output of norm is always non-negative. What if A is negative? Then you have to have absolute value for it to be positive. Then 3, if the norm of x is 0, then it means that x is 0. If x is 0, then its norm is 0. So it's if and only if. It's two-sided. And triangle inequality at the end. This is the most interesting thing. For this to understand, consider this example. Consider A, B, C, 3 points. I have these ways. So I have one way like this, one path. Another way path like this. I have a donkey here. I have some food here. The donkey wants to go toward the food. There are 2 paths. Which path does the donkey choose? A to C. Because the donkey understands that the length of AC is less than the length of AB plus BC. That's the triangle inequality, right? That's why in either Arabic or Persian, do we have Arabs or Persian people here? It's also called qaziyatul himar, which translates to the principle of donkey. Okay? Because the donkey understands it. Okay? Some important norms for a vector X. So we have norms for vector and for matrices. For vector, the LP norm is defined as this. So you have absolute value of the terms to the power of P, then the whole thing to the power of 1 over P, right? And P is greater than or equal to 1. 2 well-known LP norms are L1 norm and L2 norm. By the way, you might be wondering, why are these useful for this course? Because the cost functions are usually defined as norms. You see norms in cost functions, and we want to optimize the cost functions, right? You see this a lot. So L1 norm and L2 norm. This is if you put P to equal to 1, you will get this. P equal to 2, you will get this, right? So L1 norm and L2. As you see, in L1 norm, you have absolute value. Absolute value for 1 dimension is not as smooth at this point, right? At this point, it's not as smooth. However, this has a square like this. Squared is a smooth. L infinite norm or infinity norm or maximum norm or also called Chebyshev norm. It's defined as this, maximum of the absolute value of the elements. Okay. Now, an important norm for matrix. By the way, we have other norms too. It's out of the scope of this course, such as nuclear norm. We have these, not covering them. Okay. Important norms for matrix. The most important, I think, norm for matrix for usual optimization is Frobenius norm. It's this, defined as this. Frobenius norm, as you see, its form is the same as L2 norm for vector. So Frobenius norm for matrix, its format is the same as, similar to the format of L2 norm for vector, right? However, we have L2 norm for matrices too. Don't confuse them. But out of the scope of this course, right? So don't call Frobenius norm L2 norm. No. We have L2 norm of matrix has another definition. Okay, quadratic forms, as you see. So using the equations that we had, this is quadratic form X transpose X for vector X. But for matrix X is trace of X transpose X. And they are like balls. They are like balls. And they are, as they are quadratic, they are smooth. Preliminaries on functions. Do you remember we talked about convex set, right? Now I'm talking about convex function. Convex function. A function f with domain D. What do I mean by domain? I think you know this, right? The domain of a function is convex if this. The domain means that the argument of the function, where can it be, right? So it's like one of the definitions of convex function is this. It means that f of alpha x plus 1 minus alpha y. So this is x, this is y. Alpha x plus 1 minus alpha y, it means some point in between. We talked about it previous slides ago. T x plus 1 minus ty. So some point here in between, such as this point. Its f is here, right? Its function value. Its function value, right? Its f must be less than or equal to alpha f of x. So this is f of x, and this is f of y, right? Alpha times this plus 1 minus alpha times this should be greater than or equal to this one, this value, right? In simple words, it means that if you connect these 2 points by some line like this point should be below it. A counter example like this. This is not convex function. Consider these 2 points. This point is above. You see that? You see that? By the way, why are you confused? No? Let me know if I need to explain again. Tell me. No? Okay. F of x is another definition. So that there are several definitions for convex function. This is the second definition for convex function. Convex. If f of x is differentiable, it means that I can take derivative. It is a smooth. Okay. Then this is another definition. Here I use the derivative of f transpose x minus y. In simple words, consider this function. Consider this function. A tangent line to this at point y, its equation is this: f of y plus gradient of f at the point y transpose x minus y. Why? Why is it like that? Because we know that derivative is the slope of the tangent. Okay. F of x here should be above this line. Above this line. Above this line. Here it's above it. If it's not above, then it's not convex. Either of these definitions you use, you can find out whether a function is convex or not. A third definition of convex function is this. When you can calculate the second derivative should be facing up. Do you remember? Several minutes ago, before the break, I said the first derivative, the second derivative means that where the ball is facing, whether upwards or downwards. A counterexample, this is not a convex function. Why? Because some region of it is facing downwards. These two are facing upwards, but some region is facing downwards, right? In simple words, so I told you 3 definitions of convex function. Forget them now. In simple words, the function, if it's like this, is convex. If it's like this, it's non-convex. Okay? As you see, convex function is very easy to optimize. Hence, it's related to optimization. Why? Because in convex function, you can easily find the minimum. However, when it's non-convex, you have several local minimums. You have, for example, here 2. Right? when it is convex function, what? Semi-definite means that its eigenvalue, as it is multi-dimensional, this Hessian is a matrix, okay? The second derivative is a matrix. I will talk to you about that later in a few slides. But it is a matrix, and the matrix can be either positive. Here, if it is a positive semi-definite, then it's convex. But what does positive semi-definite mean? Positive definite means that all of its eigenvalues are greater than 0. Positive semi-definite means that all of its eigenvalues are non-negative. They can be 0. Some of them might be 0. 0 or positive is positive semi-definite. Only positive, not 0 at all, means positive definite. Okay. In simple words, why do I use positive semi-definite? Because this is positive definite, but this is positive semi-definite. Both of them are convex. Both of them are convex. By the way, if it is negative definite, means like this. We call it concave, the opposite of convex. For maximization, you want it to be concave. For minimization, you want it to be convex. Okay. Now I think the cooler parts. These are more cool. So preliminaries on optimization. So we have minimum, maximum, infimum, supremum. I think you have heard of this a lot, right? Let's define them once forever. A minimum and maximum of a function f. So consider a function f. It takes a d-dimensional input. It outputs some scalar. F, you can see it as a map of x to f of x, right? With some domain d. The minimum of the function x with respect to x is less than f of y for all y in the domain. For all of the points in the domain of the function, when you calculate the function value of x is less, the lowest. Like this. Consider this. The function value of this point is here, right? The function value of this point is here. F of x, f of y. F of x is less than f of y, right? Less than or equal. Why? Because, for example, consider this function. All of these are minimum. All of these are minimum. The other way around is maximum. When for all of the points in the domain, that function value is greater than or equal to, like this. This is f of x. This point is f of y. F of x is greater than f of y. Why greater than or equal to? Because all of these are maximum. Right? I think minimum and maximum are obvious. But usually, I don't know why. When people hear supremum and infimum, they get scared. It's very easy. Infimum and supremum are these. Nothing but minimum and maximum. So you can see infimum as minimum, supremum as maximum, with some difference, I will tell you. Is that infimum and supremum are more generalized than minimum and maximum. In what way? In this way. That they accept this. What if the function value never reaches something? What is that in English, the word in English? What? Asymptote, right? Yeah. What if you have asymptote? Does this function with asymptote have any maximum? Never reaches the maximum. If you say this point is maximum, no. If you go further, you'll see a value, function value higher than that. You never reach that, right? Then we don't call it maximum. We call this supremum. What if you have asymptote in this way? It's going down, but it never reaches the minimum. Then this is called infimum. Right? And here we also have said that consider z less than or equal to f of x like this, less than this value is less than or equal to f of x. So what does this mean? It is a lower bound, right? Lower bound of the function. But the maximum lower bound. So bring up the lower bound up to it reaches the function. It's exactly the asymptote, the definition of asymptote. This is infimum. Supremum is the other way around. What is this? This is upper bound, where z is greater than or equal to f of x. What do I mean by upper bound? Assume this is a function. All of these are upper bound. Bring the upper bound down as much as possible until it reaches the function as an asymptote. Then it becomes supremum. The minimum, bring it down, up. Right? That's why in optimization, usually they use infimum and supremum rather than minimum and maximum. Why? Because they want to cover all cases. They want to cover all cases. Because if the function doesn't have any asymptote, infimum reduces to minimum, is equivalent to minimum. When there is no asymptote in a function, monotonic function which is going up, then the supremum is equivalent to maximum. Right? Any question?
If the asymptote is vertical,
Vertical. Yes, so exactly like this. Like this. In this case, we don't have any maximum. We don't have also supremum. Or maximum or supremum is infinite. When you have a vertical asymptote. This is related to, I just tell you, I have eliminated some concepts because I didn't want to frustrate you. But if I want to tell you just for those of you who are interested, who want to learn more, you can take a look at Lipschitz continuity or Lipschitz smoothness. This is related to Lipschitz smoothness. Lipschitz smoothness says how much slope my function can have. The slope here goes to infinity, the slope. So it's not a Lipschitz smooth. Out of the scope of this course, just for interested students.
so it wasn't a supremum?
What? No, here we don't. The supremum or the maximum, they are equivalent and they are infinite. Right?
Infimum wants it to minimize. And that only shows supremum because no matter how far you go, it will always be higher.
Yes. So it goes up until infinity. Right? Therefore, the maximum is infinite. Right? Okay. Now, local and global minimizers. Local minimizer, it means that for a neighborhood around the point like this, for a neighborhood around it, it's minimum. This is local minimum. For a neighborhood around it, it's maximum, it's local maximum. Right? You understood it in English. Now let's understand it in mathematics. What is this? Don't be scared of these notations. These are very easy. You need to just focus and understand. What does this mean? This is the opposite E, right? E in English. It means that there exists. At the best. Yes.
Higher dimensional function, like would they in supremum always be like a n-1 dimensional space? Or
Yes.
It's always n-1 or
I believe it's n minus or d minus 1. Yeah. If you say it's a d in a d dimension. Yes. 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 So the question is, what is the dimensionality of this asymptote? It's if the dimensionality of the function, if the variables is d-dimensional, then the asymptote is d minus 1 dimension. For those of you just an example here. Let me think. Yes, here I think for in 3D you understand it better. Consider some, how should I draw it? Something that goes up and down, so it's yeah. Oh, no. If the optimization variable is d-dimensional, then the asymptote is d-dimensional also, because the last one is f, the cost value. Okay, here it is 2D, x1 and x2. Okay, then the upper bound is a plane. Do you agree? So the plane is also 2D. So the dimensionality of the asymptote is the same as the dimensionality of the x's, the input. Again, I don't want to scare you, but just for those of you who are interested, this is related to algebraic topology. Okay? For those of you who are crazy for math, this is related to the dimensionality of these things are related to algebraic topology and a little bit differential geometry. Okay. Anyway, does it answer your question? Okay, great. So I was explaining this equation 4. I want you to understand the mathematical expressions, and they are very easy. When you have E, this means there exists, because exists starts with E. This means for all, because all starts with A, and this is the reverse A. For all, and there exists, right? So it means that there exists some epsilon greater than 0. And usually when we say epsilon, it means that it's a small positive value, right? That for all of the points y in the domain, the L2 norm of y minus x, it means that the distance of y minus x is less than or equal to epsilon. What does it mean? It's neighborhood. It's neighborhood, right? The point is very close to that point with the distance epsilon at most. Then f of x should be less than or equal to f of y. For any neighbor point y around x, f of x should be less than f of y. Means local minimum. And global minimum or global minimizer, it means that for all of the points in the domain, the whole domain, not just in a neighborhood, I should be minimum. Here, this is global minimum. This is global maximum. We might have several global maximums here, which are equal to each other. And this is the saddle point. Okay. There is some lemma. In a convex function, there is no proof. As you see, I have eliminated the proof. For those of you who are interested, you can take a look at my tutorial for the proof. Okay. But try to understand it. Try to understand this lemma. It says in a convex function, any local minimizer is a global minimizer. I think it's obvious. Consider this convex function. Consider this convex function. This is the local minimizer, local minimum. This is also the global minimum, right? However, this doesn't hold for non-convex function, such as this. This is a local minimum, but this is not a global minimum, right? This case, it is convex, but it is not a strongly convex, okay? This is a strongly convex because of this. In this case, we have several local minimums and several global minimums. So we might have several global minimums, but their function value should be the same. What is this? This is called first order condition. Exactly what I said in several minutes ago. I asked you guys, when you have an unconstant optimization problem, you want to find its minimum or maximum. What do? We learned it in high school or college. Take derivative, set it to 0. This is exactly what it says. It says that in a minimum or maximum, the derivative should be 0. This is called first order condition. That also has a proof. we have a stationary point. A stationary point, the gradient is 0. So whenever it is minimum or maximum, the gradient is 0. But when the gradient is 0, it's not necessarily the minimum or maximum. It might be the saddle point, right? So it's just one-sided. So what do I mean? These, all of them, gradient of f at them is 0, right? These points are all called stationary points. The stationary point might be minimum, might be maximum, might be saddle point. Okay? Again, if X is a local minimizer, according to first order optimality condition, the derivative is 0. As I said before, if we can find a closed form solution, the optimization is done. It's finished. You don't even need classical optimization. You don't even need metaheuristic optimization. You need metaheuristic optimization when you can't solve it easily, right? What is argument of optimization? I think you have seen this a lot. So you see minimum of f of x, mean of f of x. Sometimes you say argmin of f of x. What is the difference? What is the difference? So the difference is this. Here in this function, consider this function. This is the equation of the function. What is the minimum? Can you tell me? This is 2, right? The minimum of f of x with respect to x is 2. However, argmin is this. The argmin of f of x with respect to x is 1. Because at the argmin means which x. At which x it is minimum. Minimum of f of x, it means that what is the function value at the minimum. We have the same things for max and argmax. Maximum, argmaximum. We have the same thing for arginfimum, argsupremum. By the way, if it is if it goes like this, its argsupremum is not defined, right? Or it might be infinite. However, if it is like this, its argsupremum is this x. Okay. Now back to what we talked about. When we have a minimization problem, we can convert it to maximization, or vice versa. There are at least 2 ways. Can you guys tell me without looking at it? I have maximize f of x. How can I convert it to minimization problem? One way is what? What? One way is inversing, exactly. Reciprocal, right? So rather than saying maximize f of x, you can say minimize 1 over f of x. One way is reciprocal or inverse. The other way is, you were saying, I guess. Another way, I said it several minutes ago as an example. Exactly, you put negative signs behind it, right? Maximize f of x, you can say minimize minus f of x. Let's see this. Here, maximize of f of x. Right? Maximize of f of x, you can see it as minus minimize of minus f of x. So this is the minus that we talked about. Why have I put minus here again? Because, let me tell you. Assume this is f of x, right? Consider this example. I multiply the cost function by minus 1, so like this. So it becomes like this, right? Comes like this. I find this minimum. So I solve the minimization problem. It gives me minus 30. However, the maximum is supposed to be 30. So I have to multiply it by minus again, the cost. Right? Likewise, minimize f of x, you can see that minus, maximize minus f of x. However, what if I don't care about the function value, optimum function value? I care about the argument. If you care about argument, you don't need that minus anymore. The function value is not important. Both of these 10 is the argument of the optimum. Right? Right? That's why in neural network, in deep learning, you want to maximize log likelihood, you minimize minus log likelihood. At the end, you never multiply by minus 1 again. Just 1 second. Because the weights which are the arg mean or argmax are important. The weights of the neural network are arg mean. You were saying. Log likelihood. What is that? Okay, I'll tell you briefly. Although it's a bit out of the scope, but let me tell you. So when we say likelihood, it means that you can see it as probability. But consider the Bayes rule. The Bayes rule, probability of, just give me a second. Y, probability of y given x equals probability of x given y, probability of y over probability of x. Sometimes they call it likelihood, and they call this posterior. Anyways, you can see likelihood as probability, right? So you can say, I want to maximize the probability of data. Which optimization variables maximize? However, in neural network, you can't maximize. You need to minimize. Therefore, you use these techniques. As in neural network, argument is important. We don't multiply by minus 1 again, the cost value. Another thing is the reciprocal or inverse. If the function value, optimum function value is important, again, I need to do the reciprocal again. Right? If the argument is important, I don't do it. I don't do the reciprocal as the inverse again. Like this, an example. This is f of x equals x squared. I want to it's a minimization problem, but I want to convert it to maximization problem. 1 over x squared is like this. What is its maximum? Its maximum is infinite. What is its argmax? It's 0. Argmax is found. If minimum is important to me, the min f, then I need to have 1 over infinite, which is 0. Right? Right? This is a very beautiful thing. Just focus to. I know it's almost the end, but let me say this and we'll finish. It's very beautiful. What is the derivative? What is the definition of derivative that we learned in high school? In derivative, we say, when I say derivative of Benjamin with respect to desk, it means that let me change the desk and see how much it affects Benjamin. Right? It's exactly like the definition of derivative. When I say definition of something with respect to another thing, it means that let me change that another thing. How much does it affect or change or impact that thing? Okay. So when I have a function, its input is a scalar. Its output is a scalar. The derivative of function, which is a scalar, with respect to a scalar input, should be a scalar. Why? Because when I tweak that input to scalar, it only changes that function once, right? I tweak it a bit, it changes it. I tweak it a bit, it changes it. So these changes the scalar itself. Therefore, the dimensionality of derivative of a scalar with respect to another scalar is a scalar. right? Now let's become a bit more complicated. My input is a vector. My function value is a scalar. So before input was the scalar, output was a scalar, it was high school. Now we are in university. Input is vector, function is a scalar. Derivative of a scalar with respect to a vector. Let's analyze it. I have some vector. It had several elements. Assume 4 elements here. I have some f which is a scalar. Let me tweak this one. It changes this a bit. Now let me don't change the other ones. Only change the second one. It changes this again. Now let me only change the third element. It changes this again. Fourth element, it changes this again. So how many changes do I have? 4 changes. So this was vector, 4-dimensional vector. This is a scalar. Derivative of a scalar with respect to a d-dimensional vector is a d-dimensional vector. Right? Because I have d elements, I change them, they tweak the function value, which is a scalar. How many cases do I have? D cases. So the derivative itself becomes a vector. We usually call a vector derivative gradient. Okay. Let's make it a bit more complicated. Assume I have a matrix as input. My output is a scalar. Let me change each element of the matrix one by one. Each change will change the scalar output once. How many changes do I have? A lot. Assume my matrix is D1 by D2. How many changes do I have?
4.
D1 times D2. Assume I have 2 by 3 matrix and 1 scalar. How many changes do I have? 2 times 3, 6 changes, right? Therefore, the derivative, you can see it as a 6-dimensional vector or as a 2 by 3-dimensional matrix. Therefore, derivative of a scalar with respect to a matrix is again a matrix. You see that? Now, let's make it a bit more complicated. My input is vector. My output is another vector. My input is 2-dimensional vector. My output is 3-dimensional output. Let me change this one. It will tweak all of them in the output. Now let me change this one. It will tweak also all of them. How many changes do I have? 6, 2 times 3. Therefore, derivative of a vector with respect to another vector is a matrix. Is a 2 by 3-dimensional matrix. I think now we can understand the dimensionality of derivative. Derivative of a matrix with respect to a vector, or what the other way around. Derivative of a vector with respect to a matrix. What is its dimensionality? Rank 3 tensor. You understood now the meaning of derivative. And when it is a vector gradient, when it's a vector derivative, we usually call it gradient. Okay, we will continue in the next session. 9:20 was the end, right? Yeah. Thank you. Thank you.